Hi, Algebra 2 honor students. This is the last day of Unit 10 on sequences and series. Today we're going to be talking about paying off a mortgage. And let's read that statement quickly at the top. And I'm sure that maybe many of your parents have to think about this on a daily basis, but mortgages are not just on houses. They are large amounts of money borrowed from a bank on which interest is calculated on a regular basis. And the payments that we're going to be looking at making today on a mortgage on a house are they very similar to payments you would make on a car payment or something like that. So we're going to make regular payments. They're going to be made on the amount of money owed so that over time, the principal is the amount that you start with as far as borrowing, is paid off as well as any interest on the amount owed. And, the bank's just not going to be nice and lend you the money and just say, hey, pay us back when you can. They're going to charge you interest. They're going to make money off of the amount that they let you borrow. So this is going to be a pretty complex process, but at the end of the day, it does involve a geometric series. So that's why it fits nicely into our current unit here. So here's our first example. Suppose a person takes out a mortgage for $200,000 and wants to make payments of $1,600 each month to pay it off. The bank is going to charge this person 4% nominal yearly interest applied monthly. So that last statement there, the 4% interest is a yearly rate, but it's applied monthly. And that kind of is a big deal in terms of the way that we calculate this in our payment formula. So the first part says, well, what is the amount owed at the end of the first month? Show the calculations that lead to your answer. So the amount that's going to be owed after month one is you're going to take your amount that you borrow, $200,000. And then the very first thing you have to do is you have to multiply by the interest rate. So interest gets charged on the amount that you owe. And that 4% monthly, you're going to take that 4%, which as a decimal is 0.04. And because it's applied monthly, you're going to split that into 12 equal pieces so that each month you pay a fraction of the 4%. By the end of the year, you've paid a total of 4% interest, but it's split into 12 monthly payments. Well, the way that we apply that to the $200,000 is we're going to take 1 plus that rate and then multiply it by 200,000. Okay. That's the easiest way to do it. So you could do, 0.04 over 12 times 200,000 and then add that back to 200,000 to figure out how much interest is on that principal that you borrowed here. It's the same thing as writing it this way though. 1 plus the rate, and the rate is that 0.04 over 12. From that, you'll subtract your monthly payment. So again, interest gets charged first on the amount that you borrow. Then you could subtract out your monthly payment of $1,600, and we'll see how much we owe at the end of our first monthly payment. So let's type that in, $200,000 times 1 plus 0.04 over 12. You can do a fancy fraction there if you want, but it's probably not even needed. Minus the $1,600 payment. And now we owe $199,066.67. $199,000. Okay, still owe a lot of money. So how much of the first month's payment went towards paying off the principal? The principal is the amount that I still owe the bank, $200,000, and how much of it went towards interest? So what I can do is I can take the amount that I started with and subtract the amount that I still owe. I still owe this much money, and figure out how much came off the loan from this payment of $1,600. So $199,066.67. So 200,000. 1, 2, 3, minus that last answer is $933.33. Oh man. Okay. Now remember, this is the amount that went towards paying off the $200,000, but I paid the bank $1,600 last month. So what does that mean that we paid in interest? Well, $1,600 minus what went towards the loan amount, the $933.33, is $1,600 minus that amount is $666.67. Wow, that hurts to think about, doesn't it? That you just made a pretty big monthly payment, $1,600, and you can see the split of what goes in the bank's pocket and what goes towards paying off your borrowed amount of $200,000. Now, the nice thing is that since we're basing the next month off of what I owe, you're going to start paying a little less than interest each month, and a little bit more of your payment's going to start going towards the principal. So this eventually starts to balance out a little bit more, where by the end of your loan term, you're going to be paying small amounts of interest and more of the money is going to be actually being applied towards the principal, which is that amount that you owe on the loan. Determine the amount of money owed at the end of the second month, and again, show the calculations that lead to your answer. So we know after month one we owe this, so take that last amount, $199,066.67, and multiply by the interest, which is 1 plus 0.04 over 12. Okay, from that, you'll subtract $1,600, and we'll see here how much we owe after month two. So $19,066, oops, $199,000, that would be bad. And 67 cents times 1 plus 0.04 over 12 minus my payment of $1,600 is $198,130.22. So if I want to know how much went towards paying off the loan, it doesn't ask that question actually, but let's just calculate it quick, see how it compares to the 933 number. So $199,066.67 minus 130.23. So now this amount went towards paying off the loan. So not that big of a difference, but $3-ish more in the next payment went towards paying off the total loan, which is good because that means that less of my payment went towards the interest that the bank is getting. All right. So what I want to finally do here in Part D, it says the amount owed at the end of a month actually forms a sequence that can be defined recursively. If the first term is 200,000, then define a recursive rule that defines the sequence. Think about this for a second. Look at the last calculations we've done. See if you can get a good recursive definition here. If you want to hit pause and give it a try, go for it. But I'm going to jump right into it. That for each monthly payment, AN, I'm going to take what I owe in the last month, take the last month's amount, and I'm going to multiply it by the interest rate, which is 1 plus 0.04 over 12. And then from that, subtract your monthly payment of $1,600. So this recursive sequence would model all the monthly payments as we go from one month to the next. And we do have to define, and it's given to us anyway, that the first term would be $200,000. Okay. So in terms of calculating different terms, it wouldn't be easy to figure out, how much you owe after 5 years, because that would be 60 monthly payments. And to get 60 monthly payments, we'd have to know how much we owe from month 59. Okay. But luckily, computer programs can do that pretty easily for you and give you all those calculations fairly quickly, a lot faster than we can do it out by hand. All right, if you turn to the next page, it says example 2, if a person took out a $150,000 mortgage at 5% yearly interest, why would it be unwise to have monthly payments of $500? Okay. So if we think about the 5% yearly interest, remember that if you're making monthly payments, that yearly interest rate has to get divided by 12. So if we think about what you would owe after the first month, you would take the initial starting amount you borrowed, $150,000, times 1 plus the rate, 0.05 over 12, and then from that, subtract your $500 payment. And let's see how much we owe after the first month's payment of $500. So 150,000, let me clear out the screen so it doesn't look so messy, 150,000 times 1 plus 0.05 over 12 minus the monthly payment of $500 is $150,125. So why would it be unwise to make monthly payments of $500? Well, if you look at that total, we owe more than we started with. So if I keep making $500 payments, I'm never going to pay off the loan. This amount's just going to get bigger and bigger and bigger and bigger. Okay, so that's going to be no good. We're going to have to make a larger monthly payment. And luckily, the bank usually sets up for you what your monthly payment should be. So they're not going to really allow you to pay $500. They do want you to pay off the loan, but it's going to take a long time to do so. They're also going to make a lot of money from you in interest in the process. But you can't just on your own decide, yeah, I'll just pay $500, especially in this scenario where you're going to wind up owing more than what you started with here. Okay. In this next example, we're going to start thinking about the sequence that we defined recursively from the last page. And we're going to have a formula that would calculate the amount we owe after a certain number of months explicitly. So wouldn't that be nice? Like I mentioned, if I want to know what's happening after 5 years or something like that, which is 60 monthly payments, we're going to have to extend this such that I can easily plug in 60 and make a calculation without knowing what happened in the 59th month. So if we go back to our example with $200,000 mortgage at 4% yearly interest, the mortgage payments that we have are $1,600, okay, which we know is a lot going to the interest. Let's say if we can determine how much we still owe after end payments, and to make our work easier, we're going to follow a more general model. So we're going to let the following variables replace what we have. We're going to have R as the rate, which is the 0.04 over 12. P is for the principal amount. That's what we're borrowing to start. And then lowercase m is going to be the monthly payments that we're making. And you can see how I've kind of detailed each of those. So explain what this calculation means. If I do P times 1 plus R, so P times 1 plus R, and then I subtract M, what is that representative of? So if I did 200,000 times 1 plus the rate, subtract the monthly payment from that, that's what we did on the first page, isn't it? That was this right here. So what does that calculation result in? It's the amount owed after the first payment. So the amount owed after one payment has been made. So then what if I do this? What does this calculation represent? So I'm going to take P1 plus R minus M. Okay, if you didn't quite catch it, that's what I had in the last scenario up here. So there's that carried down. Then I'm going to multiply that by 1 plus R and subtract M from that. So this is what's owed after you make the second payment in a very algebraic, a little bit more of an abstract representation, right? And if you distribute that 1 plus R into these two terms, you're going to get P times 1 plus R squared minus M times 1 plus R minus M. So that was taking this 1 plus R and distributing it to both of those. And then based on A and B, continue this idea and write what you would owe at the end of the third month and the fourth month. I'll just do it for month 3 so we get the idea. So for month 3, what am I going to do? I'm going to take what I owe from month 2, which is this kind of large expression, P 1 plus R squared minus M 1 plus R minus M. I'm going to multiply that by the interest rate, right? This is what I owe from month 2. Multiply that by 1 plus R and then subtract M. And I really want to kind of build here what's happening in terms of the general pattern for the terms in this series that we're building. Distribute the 1 plus R, you get P 1 plus R cubed minus M times 1 plus R. If I distribute it to here, it's now 1 plus R squared minus M times 1 plus R minus M. All right, we're really building here. You can imagine that in the fourth month, what these terms are going to look like, right? So in general, after n months, what's happening is that you're starting by doing P times 1 plus R to the n power, because in month 3, that matched here, minus M times 1 plus R to the, notice how by the third month, this was only being squared, so this is to the n minus 1. If this is to the first power, this is now 1 plus R to the n minus 2, and so on and so on and so on for however many terms you have. But at the end, of course, we're going to subtract that monthly payment. And this is starting to get really abstract as we build out our case for making a payment after n months. Now, before we go on to the next page, what I want you to realize is that this term is kind of a standalone. It doesn't really fit the pattern for the rest of these. But if you look at the other terms in this series right here, they all have a GCF of negative M that we can pull out. And then we're all being multiplied by the ratio 1 plus R. So this right here is, in fact, a geometric series. And we're going to use our geometric series formula to take just this part of it and convert it into an explicit formula that we can use. So finally, if you turn to the next page, okay, we're going to use the geometric series formula and go ahead and be able to convert this into something that we are familiar with. So like I said, if you just take that end part right there, okay, forget the p times 1 plus r to the n. This is a geometric series. If you take out the negative from all these, you get m plus m times 1 plus r. This is actually written in the reverse order from what's up here. So you can see that this is the first term right here, and that each term after is being multiplied by a ratio of 1 plus r. So in a geometric series, we know the formula is S sub n equals a1 times 1 minus r to the n over 1 minus r. That's the general formula. And that's what these terms represent right here. They represent the sum of the terms in a geometric sequence. So we know what a1 is. We know what the rate is. And that's what I'm going to replace right here in this formula. Now, again, keep in mind that negative got factored out. So on the outside of the geometric series, I'm going to put a1, which is m, times 1 minus the rate or the ratio, which is 1 plus r to the n. And in the denominator, 1 minus 1 plus r. What am I subtracting this from? I'm subtracting it from p times 1 plus r to the n. So that's going to go out front. And this is the formula for calculating how much is owed after any number of months n. Here it is. That is the building of the formula for mortgage payments. That is explicit. I can now figure out after however many monthly payments I want, how much is still owed on the loan. Okay, so let's define these variables again just one more time, just to make sure that we understand what's happening here. And by the way, I have a feeling that this part of it, to get down to this step, that could have been confusing for some of you. So if you have questions, let me know in class. But at the end of the day, you do not have to memorize this formula. This would be given to you. You just have to know how to apply it given some information. So as a reminder, capital P stands for the principal, which is the initial amounts. It's what you borrow from the bank to start. R is the monthly interest rate. And I underline monthly a few times because it will always be given as, an annual rate, like, oh, it's 4% each year. You're going to take that R and divide by 12 when you plug it into the formula. Lowercase m is your monthly payment. So are we paying $1,600 a month or some other amount? Lowercase n is the number of payments that we make. And I think that pretty much covers it. Now, one last thing is that since we know that the rate is going to be a decimal that we divide by 12, I'm going to have you, oops, sorry, and this should have been a plus, guys. Sorry, if you caught that in the formula, it should be a plus as well. This rate should be the same in both those spots. I'm going to have you strongly consider storing something on your calculator, and I'm going to show you how to do this. Whatever 1 plus r is, I'm going to store that as a variable. I'm going to pick a, and you'll see what I mean in a second. So for our last example, find the amount owed on this loan after 10 years. So the loan that I'm talking about is the loan from the very first example today. The initial amount that we owe is $200,000. That's capital P. The rate we know was 4%, but then it's paid monthly. So the rate is 0.04 divided by 12. Really common thing to forget. So make sure you divide by 12. The monthly payments, little m, is $1,600 a month. And then the last thing that we have to plug in is if we're figuring out how much we owe after 10 years, you cannot plug in 10 for n because n is the number of payments that you make. If you're paying for 10 years, that's 120 payments since we're making our payments monthly. So please make sure you plug in n equals 120. I think it's pretty clear based on what I've said there, but we got to plug in the correct number for n. Okay. So here's what I'm going to do. Here's my suggestion earlier. Every time I have 1 plus r, which is here, here, and here, I have 1 plus r in 3 places. It's going to get pretty messy if I type that into 3 different locations. Considering that, what does 1 plus r really look like? 1 plus r, that quantity, is 1 plus 0.04 over 12. And what I'll tell you is that you can actually take this expression right here and store it as a variable on your calculator, which I think is just so fantastic that we have that ability. So if I take 1 plus 0.04 over 12, that quantity, what I want you to do is find the button at the bottom next to kind of the 1 down here. Mine actually is kind of rubbed off a little bit, but it should say stow on your calculator for store. If you hit that stow button, an arrow pops up. And what do I want to store this as? Well, you can store it as whatever letter you want. To get the letters, we know we're going to use that alpha key. So I'm going to do alpha A, which is that math button. So if I store this value of A, it took this as a decimal, 1.003 repeating, which is what that is, and it stored it as A. And now every time I go to type in A on the home screen and hit enter, it knows it's that number. So instead of plugging this in, if I define it as being stored as A, the way I'm going to calculate what's owed after 120 monthly payments, which is A120, would be take P is 200,000, times 1 plus R, 1 plus R is A, to the n power, remember n is 120 in this example, minus, let's go back up to the formula, we need M. M is the monthly payment of 1,600. Times parentheses, 1 minus 1 plus R. 1 plus R, that's A again, to the n power, which is 120, all over 1 minus 1 plus R. And since 1 plus R is stored as A, notice how the 1 plus R that appeared in those 3 places in the formula up top are now replaced by A. Do you have to do that? Absolutely not. Could I type in 1 plus 0.04 over 12 every time I'm in that spot? Sure. It's going to make your life so much easier. Okay. When I go to type this in, I already have that stored as A. Here's what I'm going to do. I'm going to do fancy fraction. Actually, not yet. Sorry. I don't have the fraction part yet. I have to type in this part first. 200,000, 1, 2, 3, 4, times A to the 120th power. Get down from the exponent, minus, now I'm going to do fancy fraction for the geometric series part. So minus 1,600, parentheses, 1 minus A to the 120 over 1 minus A. Takes a little while to get comfortable using that stored variable as stored calculation as A. But once I have that typed in, it matches exactly what I wrote down. Here is what you would owe after 120 payments. Okay, so make sure it doesn't go up because we've made a lot of payments here. But we still owe $62,566.85. Seems like still a lot of money. We've paid for 10 years, but we still owe that much on our mortgage. Okay, and I would say, to be completely honest, these are very typical numbers. Okay, so I realize there's a lot of information, a lot of new vocabulary being thrown your way, but this is pretty much as real life as it gets. So we will do more practice using this formula next time we are in class. Let me know if you have any questions about the derivation and about how we stored these values and plugged it into the equation. Have a great rest of your day.